So in today's class, we will first solve a numerical problem related to the application of Schrodinger wave equation to particle in a one-dimensional box. So I have written the question. An electron is confined to move in a length of 1 nanometer. You are supposed to calculate the 0 point energy of the particle, and the second question is how much energy is required to promote the electron to the next state. So let us solve one by one. Okay, so clearly this is an example of a particle trapped in a one-dimensional box. So they have mentioned what the particle is. The particle is an electron whose mass is 9.1 into 10 to the power minus 31 kg. So though the value of mass is not given, you should know it, okay, because it is a universal value, a standard value, mass of electron. Okay, and also they have mentioned what is the length of the box. The length of the box A is 1 nanometer. So let us first write down what values are given. So mass is known, it is 9.1 into 10 to the power minus 31 kg, okay, because it is an electron. And also we know what is the length of the box. It is 1 nanometer, which is 1 into 10 to the power minus 9 meter. Okay, so since the system is the particle trapped in a one-dimensional box, we know what is the expression for its energy. The allowed energy En is given by the formula n square h square divided by 8m a square, where n stands for the quantum number whose value is 1 to 3 and so on. Okay, so let us consider the first question. What is the 0 point energy? Okay, so in the last video I defined what is 0 point energy. So 0 point energy is the lowest energy the system has or the particle has, and in this case the lowest energy corresponds to n is equal to 1, because the lowest value of n is equal to 1. So for 0 point energy, okay, so for 0 point energy n is equal to 1. So therefore 0 point energy E1 is 1 square into h square. H is Planck's constant, it is 6.626 into 10 to the power minus 34 joule second. Its square, okay, it is h square divided by 8 into mass 9.1 into 10 to the power minus 31 kg, mass into a square. What is a? It is 1 into 10 to the power minus 9 meter square. Okay, you can calculate this yourself. Okay, the answer is 6.025 into 10 to the power minus 20 joule, okay, which appears as a very small number because 10 to the power minus 20 is such a small number. So this number looks very insignificant, but okay, it is not an insignificant number, it is a significant number considering the mass of electron. See, mass of electron is very less, 9.1 into 10 to the power minus 31 kg. So considering the mass of the electron, this energy value is not insignificant, it is a significant value. So now let us try to answer the second question. How much energy is required to promote or to jump the electron to the next state? So let us try to understand this diagrammatically. Okay, so initially the particle is in its ground state, so the electron is in the state corresponding to n is equal to 1, which represents the ground state, where its energy is E1, that is the 0 point energy. The next allowed state is corresponding to n is equal to 2, where the particle has energy E2, which is 4 times E1. Okay, so E2 is equal to 4E1. Okay, that I have discussed and proved it in the last class. That is the energy of the particle in the second state is 4 times the energy in the ground state. So how much energy is required to promote the electron to the next state? So what they are asking is, to promote this electron to n is equal to 2 state, how much energy is required? How much energy is required? That energy required is nothing but numerically equal to the spacing between these two energy levels, which is E2 minus E1, which is equal to 4 into E1 minus E1, which is 3 into E1. So the energy gap between these two states or these two energy levels is 3 into E1. The particle is already having energy E1. If I supply additional energy 3E1, then it is promoted to the next state. So 3 into E1 amount of energy is required to promote the electron from the ground state to the next state. So this is the second problem. So therefore, amount of energy required to promote the electron from n is equal to 1 to n is equal to 2 state is delta E is equal to E2 minus E1, which has worked out to be equal to 3 into E1. How? That I have shown here. So delta E, that is the amount of energy required to promote the electron, is 3 into E1, and already we have found out what is the value of E1. So therefore delta E is 3 times E1, 6.025 into 10 to the power minus 20 joules. If you work out, it becomes 18.075 into 10 to the power minus 20 joules, or you can also write in terms of okay, you can keep it like this. It is 18.075 into 10 to the power minus 20 joules of energy is required to promote the electron from the ground state to the first excited state. Okay, so these are the solutions to this problem. So now we will shift to our discussion to a new topic, that is the application of Schrodinger wave equation to a particle trapped in a three-dimensional box. So earlier application was a one-dimensional problem where the particle was allowed to move in a one-dimensional region of length A. Now the particle is allowed to move in 3 dimension. Okay, so the final results that we get are the results are already known to you. It is not a new topic. One dimensional box we ಏನು discuss ಮಾಡಿದ್ದೇವೆ, similar results will be appearing for the 3 dimensional box, but still we are studying this because if we know the solutions to a one dimensional system, then it is mathematically easy to extend those solutions to a 3-dimensional system. Why? Because in terms of mathematics, it is always easy to handle and work out mathematical equations related to one dimension, because we have to work with lesser number of variables or parameters. Then you 3-dimensional problem or 3-dimensional system ಬಗ್ಗೆ discuss ಮಾಡಬೇಕಾದ್ರೆ you have to work out with more number of parameters, so the complexity of the mathematical equations will be more in 3 dimension. But what we will see here is, if we already know the solutions to the one-dimensional system, it is easily possible to extend these solutions to a 3-dimensional system. So therefore we are discussing this application of Schrodinger wave equation to particle in a 3-dimensional box. Okay, so now let us apply the Schrodinger wave equation to particle in a 3-dimensional box. So shown here is the representation of the system, that is a particle of mass m trapped in a 3-dimensional rectangular box. So again, the particle is a free particle. What do you mean by a free particle? No force is acting on the particle, and if no force acts on a particle, the potential energy of the system remains constant. Okay, and just we treated potential energy as equal to 0 in the one-dimensional box. Here also we are treating the potential energy as equal to 0. That is for all that is purely based on our convenience. So it is for our convenience that we are assuming that potential energy V is equal to 0. Okay, so inside the box which is specified by this condition, the value of x, okay, value of the position of the particle x along x-axis should be greater than 0, and it should be lesser than or equal to a. Similarly, along y-axis, the value of y should be greater than or equal to 0 and less than or equal to b. Similarly, along z-axis, the position of the particle z should be between 0 and c. So this represents the region or space inside the box. So inside the box, potential energy is equal to 0. Outside the box, region outside the box, which is specified by this condition, x value, that is the position of the particle along x-axis, is less than 0 or greater than a. Similarly, the position of the particle along y-axis, y is less than 0 or greater than b, and along z-axis, the position of the particle along z-axis, z is less than 0 and greater than c, and greater than c, okay, which represents the region outside the box. The potential energy is equal to infinity, okay. And why we are inserting this condition of infinite potential, okay, because if an infinite potential is present outside the region, then we can imagine the walls or the boundary of this three-dimensional box to be made of infinite height, okay. So the particle, if it has to cross this wall, if it has to cross this barrier, it has to gather or accumulate infinite potential energy, which is not possible, okay. Practically it is not possible. So what we are doing is we are confining or restricting the particle to remain inside the box by setting this condition that V should be equal to infinity outside the box. So here I have shown a particle of mass m which is trapped inside a three-dimensional rectangular box, okay. What do you mean by rectangular box? The height, the length, width and the breadth of this box are not equal to each other. They may be equal or may not be equal. So A is not necessarily equal to B and not necessarily equal to C, okay. Such box, a three-dimensional region, is called as a rectangular box. So the dimension of the box along x-axis is A, as I already told you. The length of the box along y-axis is B, and the height of the box along z-axis is C. So the total volume of this region can be written as V is equal to A into B into C, and the particle can move along any axis. It can move along y-axis, or it can move along x-axis, or it can move along z-axis. So this represents the particle trapped or confined to move in a three-dimensional rectangular box. So this is the definition of the system, that is particle in a three-dimensional box. Now let us apply the Schrodinger wave equation to this particular system. So we will begin with the general Schrodinger wave equation. So since this is a three-dimensional problem, we have to use the three-dimensional Schrodinger wave equation. What is the three-dimensional Schrodinger wave equation? The general form of three-dimensional Schrodinger wave equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square, okay, plus 8 pi square m by h square into E minus V into psi is equal to 0, okay. This is the general three-dimensional Schrodinger wave equation. I hope you have not forgotten this, okay. We had derived this equation probably 2 weeks before, where psi is, okay, actually depending on the position of the particle along x, y and z axis. So psi is equal to psi of x, y, z, which represents the wave function of the particle inside the box, and it represents the state of the particle inside the box. Now let us apply the condition that is applicable for the three-dimensional box. What is the condition that is applicable for a three-dimensional box? It is here, shown here, that inside the box, within the box, the potential energy of the particle is 0. So if I insert this condition, V is equal to 0 here, then it is possible to write the corresponding Schrodinger wave equation for particle in a three-dimensional box. Therefore, for the particle within the box, V is equal to 0. So the potential energy V is equal to 0. Therefore, dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into E minus V is 0. So into psi is equal to 0. So this is the three-dimensional Schrodinger wave equation for particle in a one-dimensional box. So this is Schrodinger wave equation for the particle in the 3D box, trapped in the 3D box. This is the general three-dimensional equation. This is the equation exclusively applicable for the three-dimensional box. This is a partial differential equation. Equation number 1, that is Schrodinger wave equation, is a partial. It is a partial differential equation containing how many variables? It contains 3 variables, x, y and z. That is the position along x-axis, y-axis and z-axis. Now there are different methods for solving such partial differential equation, and one simple method and the most frequently used method in quantum mechanics, or at least in the earlier stage of this application of Schrodinger wave equation, is called the method of separation of variable, right? So equation 1 is solved by method of separation of variable. As the name suggests, separation of variable, we are trying to separate variables from one another. Which are the variables? I already told you, the 3 variables are x, y and z. So we are trying to separate the 3 variables from each other. This is possible. Okay, the separation of variable is possible if we assume that the 3 variables are independent of each other. Yakandre, if the variables depend on each other, then it is not possible to separate the 3 variables. So if we want to separate 3 variables, it should so happen that the 3 variables should be independent of each other. What does it mean? Physically, what does it mean? It means that the movement of the particle along x-axis should not disturb its motion along y and z-axis. Similarly, the motion of the particle along y-axis should not disturb its motion along x and z-axis, and same thing applicable to z-axis. The motion of the particle along z-axis should not disturb its motion along x and y, and vice versa. Okay, so if we assume that the 3 variables are independent of each other, x, y, z are independent, that is the motion of the particle along the 3 axes do not affect each other, then it is possible to apply this method called as separation of variable. So the key step and the first step involved in the method of separation of variable is to write the total wave function, okay, psi, which is nothing but psi of x comma y comma z. This psi of xyz is the total wave function representing the overall motion of the particle along x, y and z axis, and this function is factorized or split into product of 3 functions. It is written as psi of x into psi of y into psi of z. Okay, so this is the key step in the method of separation of variable. The overall wave function is now written as product of 3 wave functions. Psi of x is the wave function corresponding to variable x, which represents the state of the system or the state of the particle when it is moving along x-axis. Psi of y is the wave function along y-axis, which describes the motion of the particle along y-axis, and psi of z represents the state of the particle moving along z-axis. So the first function depends on one variable, second function depends on the second variable, and third function depends only on the third variable. So the overall wave function, which is dependent on three variables, is now factorized and written as product of three functions where each function depends only on one variable. Okay, so this is the first and the key step in the method of separation of variable. And when we write the wave function like this, the total energy of the particle E, okay, the particle has energy, okay, and all that energy is in the form of kinetic energy. Why? You already know, because the potential energy of the system is 0, so all the energy of the particle should be in the form of kinetic energy. So the total energy of the particle can be written as sum of the energy of the particle due to its motion along x-axis plus Ey, that is the energy of the particle due to its motion along y-axis, plus Ez, that is the energy of the particle due to its motion along z-axis. Okay, don't confuse the meaning of Ex, Ey and Ez. Ex does not mean that the energy of the particle depends on the position x, or Ey does not mean that energy depends on the y position of the particle. Adiriti, similarly, Ez does not mean that energy of the particle depends on the position of the particle along z-axis. Ex means it is the energy of the particle when it is moving along x-axis. Similarly, Ey and Ez means the energy of the particle when it is moving respectively along y and z axis. So remember this step, wave functions are always multiplied, energies are always added. You cannot multiply energy, okay? Energies are always added. Now if we substitute these two conditions, okay, this is equation 2, this is equation 3. So if I substitute equation 2 and equation 3 in equation 1, okay, here I have psi, which is psi of xyz. Instead of psi of xyz, I can write this form, psi of x into psi of y into psi of z. So each psi term here is replaced by equation 2, that is psi of x into psi of y into psi of z, and energy term here is replaced by Ex plus Ey plus Ez. So let us substitute equation 2 and 3 in equation 1. Okay, we will skip all the mathematical steps that are involved. So we have to make some rearrangements. We take some derivatives. You have to apply the rules of partial derivatives. Okay, we will skip all those mathematical steps and we assume that we have done all this arrangement. I will give the final equation. Okay, so what happens is, substituting equations 2 and 3 in equation 1 and making suitable mathematical rearrangements, okay, by making some rearrangements, the three-dimensional equation 1 is divided into three one-dimensional equations, each equation dealing with one variable. This is interesting result. So what we have done is, by applying this method of separation of variable, we have converted a three-dimensional equation, a three-dimensional problem, into how many one-dimensional problems? It has been divided or converted into three one-dimensional equations or one-dimensional problem, each equation dealing with one variable. So what are the three equations? The three equations are, so when I substitute these two in this equation 1 and make some rearrangements, I get these three equations: d square psi of x divided by dx square plus 8 pi square m ex into psi of x divided by h square is equal to 0. This is the first equation. Similarly, d square psi of y divided by dy square, that's 8 pi square m into ey divided by h square into psi of y is equal to 0. The final equation, d square psi of z divided by dz square plus 8 pi square m divided by h square into ez into psi of z is equal to 0. Okay, so what we have done is the three-dimensional problem or the three-dimensional equation, Schrodinger wave equation, is converted into three one-dimensional problems. And if you carefully look at equation number 4, this is nothing but the Schrodinger wave equation for the particle trapped in a one-dimensional box. We had discussed this in our last class, and there we had seen this equation. This equation number 4 is nothing but the Schrodinger wave equation for the particle trapped in the one-dimensional box along x-axis. So we need not again solve this Schrodinger wave equation because we have already solved it. One-dimensional problem, we have already solved it. Therefore we know what is the solution for this equation, what is the expression for energy and what is the expression for wave function is already known, so we need not solve it again. So this is the utility of the method of separation of variable. Though this equation, a three-dimensional equation, looks very complicated, but what we are doing is we are simplifying this three-dimensional problem and splitting into one-dimensional problems, several one-dimensional problems, three in particular, or to be exact, three one-dimensional problems, and the solution to the one-dimensional problem is already known. Okay, so this is the Schrodinger wave equation for the particle trapped along x-axis. Similarly, equation number 5 and equation number 6 are nothing but the corresponding Schrodinger wave equation for the particle moving along y-axis of length b and along z-axis of length c. This is the Schrodinger wave equation for the particle traveling along x-axis. The length of the box along x-axis is a. This is the Schrodinger wave equation for the particle moving along y-axis. In this direction, the length of the box is b, and this is the Schrodinger wave equation for the particle traveling along z-axis having dimension c. So let us now directly write what are the solutions to equation 4, 5 and 6. Okay, we need not solve it again. We already know what should be the solution. Therefore, let us directly write what is the solution. Equations 4, 5 and 6 are the nothing but the Schrodinger wave equation for the particle traveling or moving along x, y and z axis respectively. Therefore, solutions to these equations, okay, so these are nothing but one-dimensional box problem. This is nothing but the one-dimensional problem, box problem along x-axis, y-axis and z-axis. So solution to these equations are, let us first write the solution for this equation. The expression for energy Ex, okay, it is n square h square divided by 8ma square. So I will write nx square h square divided by 8ma square, where a is the length of the box along x-axis and nx represents the quantum number specifying the particle's motion along x-axis. Okay, and okay, let me take it as equation 7. The wave function for the particle representing the motion of the particle along x-axis is square root of 2 by a, the length of the box along x-axis, into sine n x pi by a into x. So these two are the well-known equations. Okay, similarly you can write the corresponding solutions to equation 5 and 6. Ey is ny square h square divided by 8mb square, where ny square is the quantum number for the particle's motion along y-axis, b is the length of the box along y-axis. Psi of y will be square root of 2 by length of the box is b along y-axis into sine ny pi by b into y. Similarly, you can write Ez is equal to nz square h square divided by 8mc square, the length of the box. Okay, c is the length of the box along z, and psi of z is equal to square root of 2 by c into sine nz pi by c into z, where nx, ny, nz, they are the quantum numbers whose value are integer 1, 2, 3, etc. Similarly, ny is integer 1, 2, 3, etc. nz is 1, 2, 3, etc. And these values represent the state of the particle along x-axis, y-axis and z-axis. Remember, nx, ny or nz cannot be equal to 0. The first value of nx, ny and nz should be equal to 1. Why? You already know it. Okay. And also the values of nx, ny and nz can be varied independently. What does it mean? Changing the value of nx has no effect on the value of ny and nz. Why this is so? Because we had assumed that the motion of the particle along x-axis will not disturb the motion along y and z-axis. Okay. Similarly, you can give the statement for the other two axes. So changing the value of nx does not affect the values of ny and nz. Similarly, the value of ny does not have an influence on nx and nz. So you can change the values of nx, ny and nz independently. They are the quantum numbers. So these are the solutions to the individual one-dimensional Schrodinger wave equation. But our original system is not a one-dimensional system, it is a three-dimensional system. So let us now write what is the overall solution to the three-dimensional problem. Okay, the overall solution to the three-dimensional problem means what is the overall expression for the energy of the particle in the three-dimensional box, and what is the expression for the overall wave function or total wave function. For that, we have to go back again to equation number 2 and equation number 3, which are okay. Therefore, the total wave function is psi is equal to, or psi of x comma y comma z is equal to psi of x into psi of y into psi of z, which is nothing but equation 2. I have rewritten equation 2 here. Knowing what is psi of x, what is psi of y and what is psi of z from equation 8, 10 and this is 11, this is 12. So knowing what is psi of x, what is psi of y and what is psi of z from 8, 10 and 12, we can find out what is the total wave function. So therefore psi of x comma y comma z is, let us substitute, square root of 2 by a into sine nx pi by a into x into psi of y, square root of 2 by b into sine ny pi by b into y into square root of 2 by c into sine nz pi by c into z. Therefore, psi of x comma y comma z is equal to square root of, if I write these three square root terms together, it becomes square root of 2 into 2 into 2, 8 divided by a into b into c. Okay, so everything comes under a common square root of 8 divided by abc. This abc can be also written as volume v of the box. Okay, so square root of a divided by abc into sine nx pi by a into x into sine ny pi by b into y into sine nz pi by c into z. So this is the wave function, the overall wave function or the total wave function of the particle trapped in the three-dimensional box. This wave function can be used to describe the state of the system or the state of the particle trapped in the three-dimensional box of volume A into B into C. Similarly, you can find out the total energy. The total energy is therefore Ex plus Ey plus Ez. This is nothing but equation 3. Let us substitute. Ex is nx square h square divided by 8 m a square plus ny square h square divided by 8 m b square plus nz square h square divided by 8 m c square, which is E is equal to, let us remove the common terms, which is h square divided by 8m is the common factor. Okay, inside the bracket you have nx square divided by a square plus ny square divided by b square plus nz square divided by c square. This is the total energy of the particle trapped in the three-dimensional box, which depends on the mass of the particle, the quantum numbers, 3 quantum numbers, and also the length of the box along the 3 region. Okay, so this is a straightforward derivation, but what we learned here is how a complicated three-dimensional problem can be simplified, okay, by applying the method of separation of variables, where a complicated three-dimensional problem is reduced to several one-dimensional problems for which we already know what is the solution. This method is a standard method we will be using more frequently in quantum mechanics. Okay, so that is the purpose we discussed this topic. To conclude this discussion, let us just calculate what is the 0-point energy of the particle trapped in a three-dimensional box. What do you mean by 0-point energy? It is the lowest energy the particle can have, and we can make a guess that the lowest energy for the particle in this particular case is not equal to 0, right? Because already in the one-dimensional box problem we have proved it that the lowest energy is not equal to 0. So there in fact indeed exists a minimum non-zero energy called as 0-point energy. So for to calculate the lowest energy, we have to substitute the lowest value the nx, ny and nz can take. And what are the lowest values nx, ny and nz take? Each can take lowest value of 1. Nx is equal to 1, ny is equal to 1, nz is equal to 1. Therefore represents the ground state of the particle. Okay, so for 0-point energy, nx is equal to 1, ny is equal to 1, nz is also equal to 1. Therefore E111, okay, here each of the 1 represents the value of quantum number nx, ny and nz. So E111 is equal to h square divided by 8m into, okay, nx is 1, ny is 1, nz is 1. Therefore it becomes 1 by a square plus 1 by b square plus 1 by c square. So this is the expression for the 0-point energy of the particle trapped in a three-dimensional box. Definitely this is not equal to 0, so this is the 0-point energy. Okay, in the next video we will consider a special case of this three-dimensional box, which is a cubical box. What do you mean by a cubical box? The length of the box along x-axis, y-axis and z-axis should be same. That is, a is equal to b is equal to c. So when a is equal to b is equal to c, a rectangular box becomes a cubical box. Why we are studying this special case is because when the rectangular box becomes a cubical box, it gives rise to a new phenomenon, which is a purely quantum mechanical effect or quantum mechanical phenomenon called as degeneracy. So what is degeneracy and what are degenerate states could be understood if we consider this special case called as cubical box.